Hi everyone. I would like to welcome all of you to my talk about our registered report titled Assessing Reliability of Statistical Maximum Coverage Estimators in Fuzzing. I'm Dhanush Kalyanage, and this paper is co-authored with my colleagues Nelu Mattanayaka, Jack Luo, and Rahul Gopinath at the University of Sydney. Let me start with this famous statement from Professor Dijkstra that program testing can only be used to show the presence of bugs, but never to show their absence. That means no matter how long we test, we can't be 100% sure that the program is free of bugs. So we are interested to know the completeness, and we majorly use coverage as a criteria for that. As you can see in this figure, the rate of coverage accumulation usually declines. Also, the 100% coverage is also unreachable due to the scale of today's programs. Therefore, we are interested in estimating the maximum reachable coverage of a testing exercise. In this work, we focus on fuzzing that repeatedly execute target programs with a series of unexpected inputs to discover bugs and vulnerabilities. Already, there exist techniques for estimating maximum reachability in fuzzing. The pioneering technique is called STATS framework that models fuzzing as a statistical sampling process. Several classes of statistical reachability estimators have been proposed under this STATS model. Since borrowed from ecology, these are also known as species richness estimators. Now, I would like to talk about a couple of challenges in the FOSIT approaches and their evaluations. The main one is we don't know the ground truth of maximum reachability. Usually, the previous technique used small programs that reaches coverage saturation within a reasonable time. For instance, see the plot for TCAS in this figure. But the evaluation results don't generalize for real-world programs. On the other hand, for real-world programs, reaching this asymptote is nearly impossible. You can see in the other coverage curve that even after a week of fuzzing, we still see that the coverage is increasing. Also, we have identified that the reliability of these estimators are not well evaluated for fuzzing. Our approach is actually twofold. In the first part, we generate synthetic programs which can know the ground truth for maximum reachability. Any program is a collection of control flows, and any of these control flows can be represented as LL1 grammars. Here we have the grammar conversions for three main control flows: conditions, iteration, and sequence. Interestingly, we can reverse this procedure and convert LL1 grammars to recursive descent parsers. If we use complex enough grammars, we can have parsers that has complexity comparable to the real-world programs. Let's take this conversion of simple LL1 grammar for addition of digits. First, we create procedures that for each non-terminal. For example, the non-terminal D has become pass D function in here. Within those functions, we then implement all the production rules. The linear recursions, such as in the second line of the grammar, are replaced with while loops. Also, we use lookahead tokens to exactly guide the program which rule to apply. This way, we can achieve the complex parser program for the given grammar. Here are the techniques we use to control the complexity and reachability of the parsers we generate. We control the number of procedures and branching complexity with the number of non-terminals and production rules respectively. Depth and type of recursions will determine direct, indirect, and linear recursions. Also, if we need, we can include unreachable code areas with unreachable non-terminals. In these parsers, the procedures are unreachable as grammar has reachability property. We can use the expansion rules to come up with the inputs that reaches certain code area. This way, we can generate our subjects with non-ground truth reachability. In the second part of the research, we evaluate the reliability of our estimators. As per the design, the estimator performance does not depend on the sampling unit. In the stats model, sampling unit is considered to be all the inputs generated within a certain time period. For instance, in this timeline, we have started the campaign at t equals 0 and record data in r time gaps. Therefore, one interval of size r becomes a sampling unit here. However, previous researchers have used only one fixed size, such as 15 minutes, as sampling unit. Here, we evaluate reliability by changing the sampling unit size. These are some of the details about our experimental setup. For both part 1 and part 2, we use AFL++ as the fuzzer. For part 1, we will generate around 100 parsers with 100,000 average lines of code and intended to run the fuzzer around 24 hours. For part 2, we will be using 10 to 20 well-known subject programs from Fuzzbench and conduct 30 7-day fuzzing trials similar to the previous one. In our analysis, we use mean bias, variance, and the confidence bounds of them as evaluation metrics for part 1. Similar to previous work, we will leverage Welch t-test or related non-parametric test for part 2. I invite you to have a look at our preprint on archive, which can be accessed through this QR code. And I'm taking this opportunity to introduce our software engineering research group at the University of Sydney. You can visit our website through this QR code and find more about the kind of work we do. And you are welcome to reach out to us for any inquiries or potential collaborations. Uh, uh, this is the end of my talk, and as a summary, we talked about the concept of maximum reachable coverage estimation in fuzzing and its bottlenecks, uh, our proposed approach of generating parser programs with ground truth for maximum reachability, our reliability evaluation of the maximum coverage estimators, and last, our intended experimental procedures and setup. Thank you for listening.